We've learned that Couchbase exposes 6 services through a single node type and that you can scale these services independently. But what matters most is the way, or ways rather, that we deliver your data back on demand. Couchbase provides 6 ways to access data: key value operations, aggregate views, nickel queries, which are SQL for JSON, full text search via natural language queries, event-driven triggers, and workload-isolated intensive analytical queries. Let's drill into each of these a bit. Key value operations are the core Couchbase access method. You can get, insert, replace, or remove documents or subdocuments by key, either directly or using an offline-first approach through Couchbase Lite and the Sync Gateway. Let's drill into the data service a bit. The data service has 5 key components. First, a managed cache, because memory-first architecture is directly in our DNA as a product. Second, storage. Third, a persistence queue to flow data from cache to storage. Fourth, an in-cluster replication queue to support high availability by moving replicas onto other nodes. And fifth, a cross-data center replication queue to support high availability, disaster recovery, and filtered distribution scenarios. All of these queues rely on robust, shared, multi-thread pools. We'll talk about that more in a moment. So Couchbase is memory first on all fronts. Key value operations are served from the cache first, and only seek on disk if there's a cache miss, after which the missed document is then cached. The cache is managed based on most recent document use, and cache ejection can be tuned for either full ejection, which means a subsequent cache miss requires a disk seek, or value-only ejection, which leaves keys in cache and only ejects the corresponding value. Which approach is best depends on your key size, data volume, application demands, and similar factors. Now let's take a look at how documents flow throughout your clusters. Imagine you have 2. For simplicity, we'll visualize a 2-node cluster in London and a 1-node cluster in Tokyo, though you'd likely have far more nodes than this. In production, we recommend a minimum of 3 nodes per cluster. Your application creates a document and hands it to the Couchbase SDK. The SDK relies on the cluster map to pass that document to the cache of an available node in your target cluster. From the cache, at least in this scenario, which assumes configuration for both in-cluster and cross-data center replication, the document enters the persistence queue for local storage and is saved to disk. It simultaneously enters the in-cluster replication queue for memory-to-memory transmission to another cluster node, where it is also cached, then passed to that node persistence queue to be stored, though this time as a replica. And the document also simultaneously enters the XDCR, or cross-data center replication queue, to be filtered and passed memory-to-memory to a node of the remote cluster, where it is also cached and passed along for storage and replication as required. Now, all replication in Couchbase, whether for local persistence, in-cluster replication, or cross-data center replication, relies on the Database Change Protocol, or DCP. This protocol provides for no-loss recovery if interrupted, memory-to-memory streaming, and multi-threaded parallel processing. Aggregate views are a traditional way to aggregate data in Couchbase using distributed MapReduce style functions. Now with this feature, mapping functions are defined and distributed among all data service nodes. They process each document on that node to generate a secondary index. Emit functions specify the key and value for each corresponding entry in the index. These indexes are accessible via REST API, and query parameters are available to filter the results. The functions run on each data service node inside V8 JavaScript engines, and they're efficient for ongoing statistical evaluations like counts and summations. Nickel queries are SQL for JSON, giving you the familiarity of structured query language, coupled with the flexibility and scalability of JSON-based data modeling. A nickel query looks very much like a SQL query. The difference is you are querying document fields within a bucket instead of columns in a table. You have all the filtering power you expect from SQL, along with aggregations, functions, subqueries, as well as new behaviors specific to JSON, such as nesting and unnesting multidimensional fields within documents. A query might look like this. Give me 3 attributes from my customer documents, where year-to-date sales are filtered within a range, then order the results by name. Of course, while ad hoc querying is supported, just as with any database, you'll want to create appropriate indexing to optimize the speed of commonly used indexes. As you can see, the way you do this is easy and familiar, at least to anyone used to working with SQL. The resulting indexes are maintained, lock-free, and in-memory, if you choose, by the index service. If you'd like to know more right away, take our free online course, CB110, Intro to the Nickel Query Language. Let's look a bit further at how Nickel queries operate. First, your application passes a Nickel query to the cluster through the SDK. The query service parses the query, analyzes it, and plans the execution. The query service then requests an index from the index service. This may be a primary index for a full scan, which is put in place to support ad hoc querying during development, or, more likely, a secondary index specifically designed for this query. The index service responds to the query with relevant document IDs and any other indexed data. If needed, the query service then fetches additional data using the document IDs provided by the index. This fetch process is skipped if the query is covered, meaning all requested fields were included in the corresponding index. The query service then formats the results with ordering, grouping functions, and so on, and returns the results. Now, while this may be obvious, just to be clear, all this is happening among all nodes exposing query, index, and data services, not just a single node. Users understand full text search. They use it all the time. It's Google. And they want this. It's just that simple. But why pump text all around your data center just to meet this need? Couchbase Full Text Search, which is based on the open source Blebby search engine, gives you natural language query capability for the documents you've already got sitting right there in your buckets. We provide multilingual and custom text analysis on both the search and indexing sides. We support industry-standard TF-IDF term scoring and result highlighting, as well as faceting by term or numeric or date range. You can search by required, optional, or boosted terms, phrases, and prefixes, as well as common word stems. You can run compound, conjunction, disjunction, Boolean, and date range queries as well. You get all this, and your documents never need to leave your database. If you'd like to know more right now, take our free online course, CB121, Intro to Couchbase Full Text Search. The eventing service allows you to implement event-driven mutations anytime a document is updated or deleted, with no need for middleware. The eventing service allows you to write handlers expressing business rules and other behaviors related to mutations or deletions of individual documents. You can execute Nickel queries with these handlers, securely interact with remote systems via HTTP, securely read or write from other buckets, and much more. Examples of how you might use this feature include notifications related to expiring documents, issuing threshold level alerts, propagating changes to other systems, perhaps automatically enriching document data in near real time. You could trigger time-based document updates and perform cascading deletes. To a large degree, analytics on any platform boils down to long-running queries of some form. Would you like to do this using structured query language without having to pump it into other systems and transform your data into various new shapes? We've already seen how Couchbase supports multi-dimensional scalability through service isolation. The analytics service relies on our robust ability to isolate workloads to let you run both operational and analytical queries all on a single platform with no ETL required. Mutations are coordinated among Couchbase nodes using DCP, the Database Change Protocol that we mentioned a few slides ago. It's a robust technology supporting full rewind and replay of any change to your data. So highly synchronized but fully workload isolated shadow data sets, which may be anything from full bucket duplicates to tightly planned subsets, flow onto analytics nodes by tapping into your existing DCP streams. Operational queries continue running unaffected on your data nodes, while long-running computationally intense queries run on analytics nodes, with no need to pump data throughout complex ETL processes, just so you can explore and report against it. So what have we learned? Now, Couchbase is blisteringly fast because key value operations are served directly from cache, which is managed by use and ejection type. Documents are persisted and replicated via multi-threaded memory-to-memory queues running the durable DCP protocol. Aggregate views can expose statistical indexes via REST. Nickel gives you the power of ANSI SQL with the flexibility of JSON document data modeling. Natural language querying is available without having to pump your data into a separate system just to support a search box. And eventing enables event-driven document mutations without third-party middleware. Last, long-running ad hoc and computationally intense queries can be fully workload isolated, again without having to pump your data into a separate system. Next up, we'll look further into that interesting creature we keep mentioning called a bucket, and look at how buckets compare with what you may commonly think of as a database. It's an interesting discussion. Stick around.